if you can write a game in Verilog, you become magical. And that's exactly what we are doing in lab.
One of our core values when we design this game is to bring back our users' childhood memories. This is the same reason that we designed an interactive game pattern other than creating AI. This provides opportunities to reconnect people and let them have fun.
After the game loaded, the initial screen appears. Any button pushed, it switches to the game mode. This Verilog code shows that we have different layers for initial screen, and the initial screen turns off when it enters the game mode.
The basic foundation of a game is to show interactive graphics to users. To achieve that, we designed a extensible mechanism for display. We redesigned the map from the original game. The map now is more entertaining for multiplayer. The question is, how do we display this complex environment? We divided the whole map in 13 by 13 tiles. These tiles were stored in a 13 by 13 matrix. Each cell of this matrix has been assigned a number. The number represents the current status of this tile. 0 means grass, 1 means stone. Now the map looks like this, and this is how we handle the tile-based display system. In Verilog code, the map was stored in this register. It has 6 bits of data points to support up to 64 status. At every positive edge of pixel clock, which is the same one to drive VGA output, this always block will be triggered. First we check to see if the edge counter and V counter are in the map area. If they are, edge counter and V counter will be converted to tile indexes, which is X and Y. The equation will map edge counter and V counter into the address of Word, pixel by pixel. That's how we display the map. But we don't want to limit the players into tiles, so we did something different with the characters. The characters are displayed on the second layer. It's separated from the map layer so they can have their own coordinates. They can move freely in this 416 by 416 pixels area. In Verilog code, it will still map the character's image to address of memory, pixel by pixel. The difference is, it's not based on tiles, it's based on the pixel location of the characters on the screen. The workflow looks like this. It's highly extensible. If we want more layers, we can just insert it into this cycle. That's how we display the immersive user interface.
The animation of the Bomberman differs based on the Bomberman's moving direction. The code changes the image sprites based on the direction button. A timer used to change the image every 0.25 seconds to have the animation effect. In this picture, you can see the user control buttons for the game. We use the push button for player 1 and the switches for player 2. There are total 5 buttons: up, down, left, right, and place the bomb, and 1 button for restart the game.
Blocking is a very important part in our game. Next, this video will show you how well the blocking works. I can't go up if there is a break. Here I can't go left or right because there is a stone in front of me. I can't go down here. I can't go up either. Fine, I will try another way. This is a Verilog code of blocking detection. Highlight part will detect which tires the Bomberman will be.
Bomberman of P1 places a bomb in one location, and the bomb explodes after 3 seconds. The explosion animation lasts for 1 second, and here comes another bomb and explosion. This Verilog code is for locating the bomb, and at the same time set the bomb timer. This Verilog code shows how the timers work. And this is how the animation for bomb and explosion works. P1 places a bomb and P2 is in explosion zone. The bomb exploded and P2 got killed. P2 did the same thing to P1 and had the same effect. Both of the characters are in the explosion zone. When the bomb explodes, both of them get killed. This code detects the location of the Bomberman. When the bomb explodes and the Bomberman is in explosion area, the get kill signal asserted. So the Bomberman will reset to the original position. This code resets the Bomberman when they get killed. In the scoreboard, a character's life decreased by 1 every time it got killed. Player 2 got killed and the game is over. A trophy appears on P1. The game got resetted after the result switched to 1. This code shows the life board logic. Using FSM, the life of a character decreased by 1. When restart equal to 1, life score. To do this project is interesting but also challenging. We met all the problems that we have never imagined before. But in the end, we managed to solve them one after another. We make use of what we have learned in EC551 to build such an interesting game.
In the first version of our game, we encountered some display issues. Interference occurs when images overlap. The Verilog code we had was using counter for address, and everything was in the same layer. That caused interference. The counter will continue on the first pixel belongs to the image. When overlap occurs, the first pixel won't be the real first pixel of the line. That's how it happened. We solved that by using different layers, and use mapping equations instead of address counter.
In the previous version, the score decreased by 2 every time. By running the test back, we found that the kill signal remained asserted at 2 pulse edge of clock cycle. Hence, we created a counter called SB to count kill signal, and decreases the life score when the counter equals to 2. Right now, the problem is fixed by using this method.
We realized that no matter how complex we made the game's logical underpinnings, the only output the player sees are the game's graphics. Therefore, it was vitally important to us to make sure that the graphics were true to the original game. That meant making sure that we could accurately display all the sprites and have smooth animations throughout the entire game.
After receiving each player's inputs and updating the game state, the graphics engine must synchronize with the VGA clock and display the appropriate pixel color value. In order to be able to easily incorporate transparency logic and animations, our graphics are split onto multiple ROMs. Each ROM has control over 8 to 16 individual sprites. Sprites within the same ROM may not overlap transparently, but may be involved in an animation. At each frame, as we scan the image across the screen, each individual ROM determines if the current scanned pixel is in range of one of the sprites it has control over, and, if so, retrieves the appropriate pixel value at the requisite ROM address. For example, if we are scanning a region of the image where one of the players just laid a bomb, then the base tiles ROM would return the color of the bomb, while the player tiles ROM would return the color of the player's character. All sprites use the color 001010 or green to denote the background. Each ROM's return color goes into a logical unit that determines which color to send to the VGA display. This logical unit uses a priority order and whether or not the background color was returned. We have a system for implementing general animations, such as this fireball animation for when the player dies. Unfortunately, we couldn't include such animations due to resource constraint. Our first attempts to display the PNG sprites to the VGA monitor had serious bugs. The problem was a combination of incorrect ROM addressing logic and incorrect PNG to COE file conversion. The combination of these two independent errors made debugging the color screen very difficult. Finally, after much trial and error, the appropriate bit logic was found. The final code for the PNG to COE file conversion is shown here. This code scans a loaded image, converting each pixel, represented by 3 bytes, one for each red, green, and blue color values, from decimal to binary. Since the output is only 8 bits, while the input was 3 bytes, or 24 bits, we select the 3 highest bits for red and green and the 2 highest bits for blue. These bits are combined together in BGR format.